Hello everyone, in this video we'll talk about the much celebrated Black-Scholes model. I will not go over the derivation of the model, but instead I will take the model as it is, briefly talk about its influence, and then we will interpret the model by focusing on its predictions. For this video, I will assume that you know the basics of options, for instance strike price, expiration date, and how they relate to stocks. If you also know calculus, it will be a plus, but not required for this video. So here it is. This is the famous Black-Scholes model. It basically involves a set of equations that explain price of options, call options, and put options. Taking the call option price as an example, you plug in some values for variables on the right-hand side, and out comes the price of call option predicted by the model. Of course, we will talk about the variables in the right-hand side later in the video. For now, I want to briefly talk about the model's background. You should first note that these set of equations are derived using various assumptions, such as assuming that stock price moves in certain ways, and assuming that securities are priced in ways that do not offer riskless profits, no free lunch. And of course, the model is not perfect. Some assumptions are not complex enough, and options prices observed in the real world deviate from prices predicted by the model. Nonetheless, the model serves as a framework to be used when pricing options. Not only did the model spur active research about asset pricing in academia, practitioners rely on the model to understand various aspects of options, and they also build on the model through modifications for their trading strategies. For all the contributions, Myron Scholes and Robert C. Merton received the Nobel Prize in Economics in 1997 for introducing the Black-Scholes model. So that was a brief background of Black-Scholes model. And now I want to get into the model itself and try to interpret its predictions, which is actually going to be the fun part. But before interpretation, I have to spend a little bit of time to explain about the equations and the variables. And to do that, for the remaining video, to keep everything simple, I'm going to focus only on the call price option equation. So again, this is the equation for the price of call option. And first, you should note that the terms with n over here represent a function that looks like this. So for those of you who know about distribution, n is a cumulative distribution function of standard normal distribution. If you're not familiar with this term, don't worry too much about it for this video. And also, d plus and d minus is obtained by this equation over here on the bottom. If you plug all these terms into the call price equation, you're going to end up with this very long equation for price of call option. So this long equation is the same as the one you just saw before, or this one. But people like to work with this particular form in this page, so you see something similar to this in the textbooks and on the internet if you search for the Black-Scholes model. Okay, so then what are the variables on the right-hand side? Well, first of all, X represents stock price. For example, it can be Apple's stock price or Tesla's stock price. Big T over here represents total time between issuance and expiration of an option. So if Big T is 3 months, for instance, then it means that the option expires in 3 months if it was first issued today. K over here represents strike price of the option. R represents risk-free interest rate, which in practice can be obtained from returns on US Treasuries. T, small t, represents any time between 0 and big T. So if small t equals 1 month and if big T is 3 months, then you're considering a scenario where there is 2 months left until the option expires. Finally, sigma over here represents volatility of the stock. If the stock goes through wild swings like tech stocks, then volatility will be high. For stable stocks, such as Edison, sigma will be much lower. So those are all the variables in the model, in the Black-Scholes model, and once you plug in some values for all of them into the model is going to give you the predicted price for the call option. But predicting option price is not the only thing that the model can do. We can now get into the really cool parts, which is to understand how call option price changes when one of the variables changes. For instance, according to the model, how will option price change when stock volatility increases or when time passes approaching maturity of the option? Using the model, we can answer all these interesting questions now. We can start with an easy one. How will call option price change as X or stock price increases? Well, according to the model, call option price will increase in this scenario. How do we know that the model is coming up with that conclusion? Well, remember the call option price equation? If we differentiate the call option price equation with respect to x, the stock price, then the derivative equals this term that is highlighted, which is strictly positive. If you're not familiar with derivatives, then all it's saying is that according to the call option price equation, all else equal, if stock price increases, then call option price increases as well. But is this prediction true? Is this what we see in the actual financial market? Well, you can trust me when I say that the answer is yes. If you buy a call option and stock price goes up, then in general, you're going to benefit from the increase in the call option price. This is because call option contract gives you the right to buy stock of a certain company at the strike price. So all else equal, if stock price goes up, then the call option contract becomes more valuable, which means that the price of a call option will go up as well. So the conclusion here is that the Black-Scholes model is correct about the relationship between call option price and stock price. The next question is also not complicated. We now want to know how the call option price changes as K or strike price increases. Here, you should note that for each option contract, K is fixed. So in this question, we're really trying to compare prices for different option contracts with different Ks. And according to the model, call option price decreases as K or strike price increases. We know that's what the model is telling us because the derivative of call option price with respect to K is negative. So then now we want to ask, is this what we see in the actual financial market? We'll take a look at this data from Yahoo Finance. This is showing call option prices for SPY. SPY is an ETF that tracks performance of SP 500, and you can invest in it as well as trade options on SPY. As you can see, as K or strike price increases, call option price for SPY goes down. So yes, the conclusion is that the Black-Scholes model's prediction about the relationship between strike price and option price is indeed verified. Okay, now we're going to ask more complicated, more interesting questions. We now want to see how call option price changes when sigma or stock volatility rises. The Black-Scholes model actually assumes stock volatility to be fixed, but we can still use the model to gain insight into how prices will respond to volatility that is changing. According to the Black-Scholes model, call option price increases with stock volatility. And we know that to be the case because the derivative with respect to sigma or stock volatility is positive. Now, in order to verify this positive relationship in the actual financial market, I'm going to use the SPY again, and I'm going to focus on SPY's volatility and SPY's call options. For SPY's volatility, I'm going to use something called VIX. Here, you see a graph of VIX across time taken from the Federal Reserve website. VIX is an index that represents investors' belief about SPY's volatility in the next 30 days. Whenever VIX spikes up, it means that the investors are expecting some wild swings or higher volatility in SPY in the next 30 days. So that's what VIX is. And again, my goal here is to show that all else equal, whenever VIX is high, SPY's call option price will be high as well. If I can show that relationship, then it means that the Black-Scholes model's prediction is actually true. Now here, you see a graph of SPY between July of 2024 and May of 2025. Around here, where the arrow is pointing is July 25 of 2024. And on this day, SPY closed at 538.48, VIX was at 18.47, call option with 538 strike price expiring the next day was priced at $2.95. And I just want to briefly point out that all these prices were taken at 4:15 p.m. Eastern Time because that's when options stop trading. Okay, then coming back to our question, around here is April 14 of 2025. And on this day, SPY closed at 538.46, VIX was at 30.88, call option with 538 strike price expiring the next day was priced at $4.03. So as you can see, in these two different dates, SPY price was practically the same, but the main difference was that VIX over here was higher in 2025 compared to VIX here in 2024. And because VIX was higher in April 2025, we can easily see that the price of call option with same strike price is much higher in April 2025 compared to price of call option in July 2024. So the bottom line here is that yes, just like the Black-Scholes model predicts, all else equal, when stock volatility is higher, price of call option will be higher as well. So what's going on here? Well, the intuition is that when investors expect higher swings in the underlying stock, then there will be more opportunities for higher gains, whether you're betting on the upside or downside of the stock. This results in enough demand to meet the higher premium in the price of options, and therefore we observe higher option prices in the financial market. Alright, now we will examine the final relationship in this video. According to the Black-Scholes model, as T or time increases, meaning as time passes approaching big T, the time of expiration, call option price will go down. That's what the model is saying about time and option price because the derivative of call option equation with respect to time is negative. Let's now check if model's prediction is true, again using SPY. Here you see a graph of SPY over a single day. And I'm trying to show that all else equal, the price of call option goes down as time passes. Around here, where the arrow is pointing, is February 10th, 2025 at 4:15 p.m. Eastern Time. At this time, SPY closed at 604.45. Call option with strike of 604 expiring next day was priced at $1.85. Now over here represents February 11th, 2025 at 4:15 p.m. on the timeline, so exactly 1 day has passed. And at this time, SPY closed at 605.18. So as you can see, over a single day, SPY price actually increased a little bit, from 604.45 to 605.18. If you're a picky mathematician, maybe you're bothered by a slight change in SPY price because time is the only variable that's supposed to change in this example. In other words, the all else equal argument is violated here. But I'm going to say that this example is still okay to be used because the change in SPY price is small enough to illustrate the main points. So trust me when I say that everything is okay. Okay, then coming back to our example here, if you bought the call option at 1.85 or $1.85 at the end of February 10, 2025, maybe you were slightly happy at the end of February 11th because SPY price went up a little bit. But that's actually not the case. You actually would have been surprised and disappointed because the same call option ended with the price of $1.18 the next day at February 11th. So even though SPY went up a little bit because of time decay of options or the fact that option prices go down as time passes, you just lost about 36% of your investment. Now, if you're wondering if volatility had anything to do with the drop in option price, note that in between the end of February 10th and end of February 11th, VIX changed only by 1%. So this graph is showing VIX, and as you can see, VIX was pretty much flat. So the bottom line here is that just like the Black-Scholes model predicts, all else equal, option prices go down as time passes. The intuition is that as the option approaches the end, or the date and time of expiration, there is less opportunity for the underlying stock to make huge moves, either to the upside or downside. And so because of the diminishing opportunity to make big returns, investors are willing to pay less premium for option contracts, which is why all else equal, option prices go down as time passes. As a side note, if you want to be less exposed to time decay, you should buy options that are deep in the money. Coming back to our example, if you bought a call option with 570 strike price, then you would have actually made a small profit here because the effect of time decay would have been much lower. The deeper the option is in the money, the less the option will be exposed to time decay. Okay, that's all I wanted to say about Black-Scholes model in this video. Of course, the model says a lot more than what I've mentioned in this video, but the key takeaway is that Black-Scholes model is indeed one of the most influential models in finance.